We're going to start going through and looking at which sort of reaction conditions will favor SN2 versus SN1 reactions. So we want to look at what type of alkyl halides, we're going to look at the nucleophile, and then we're also going to look at the solvent. As we go through this, we do want to keep in mind the mechanism, so I am going to draw both mechanisms and talk just kind of a quick review on both. And then again, as we go through, I'm going to keep coming back and referring to these. So our SN2, remember with our SN2 mechanism, our rate determining step depends on both the concentration of my alkyl halide and the concentration of my nucleophile. For our SN1 reaction, right, this one's first order, my rate determining step only depends on the concentration of my alkyl halide. So the nucleophile is going to be a lot more important with SN2 reactions than it is with SN1 reactions. Remember, if it's not part of the rate law, changing its concentration isn't going to affect the rate. So doing a quick mechanism on this one. Remember with SN2, and I'm just going to use again the same, actually let's just use a generic NU for nucleophile. The nucleophile attacks at the same time that my leaving group leaves. Right, this one is a concerted reaction, and then because of that, I'm going to draw my transition state, but remember that the bond that we're forming between that nucleophile and the partial positive carbon needs to be completely opposite to the bond that we're breaking between that partial positive carbon and my leaving group. And then get everything else on there. So remember, this one proceeds by backside attack. Because they're happening at the same time, whatever the configuration I had initially, if it was chiral, is going to be reversed. So if this bromine was coming out at us, my nucleophile is now going back. Right? Because they're happening from opposite sides, my configuration is always going to be reversed. So this has an inversion of configuration. Right, if it was R, it's S when we're done. If it was S when we started, it's going to be R when we're done. So nucleophile and alkyl halide, both involved in that rate determining step. Nucleophile adds from the opposite side that my leaving group leaves, resulting in an inversion of configuration. With my SN1 reactions, and we'll draw the same stereoisomer. My leaving group is going to leave first, taking those electrons with it. That's going to produce a carbocation intermediate. And then we want to remember it's planar. That's important for our stereochemistry. So we have a planar carbocation intermediate. Right? Do watch for rearrangements though. We said in our last video that if you can make your carbocation more stable, that happens. So watch for carbocation rearrangements. My nucleophile then is going to add on to that carbon. Because it's planar, it can attack from either side. And then we're going to end up with stereoisomers, one where my nucleophile is in the same orientation that we started, and then one where my nucleophile is in the opposite orientation from where that halogen started. So both of those. So we get a mixture of stereoisomers. In this case, racemic, it doesn't always have to be. Remember, again, racemic means you have an equal amount of two enantiomers. So SN2, one step, right? Nucleophile adds as the leaving group leaves, so they have to be from the opposite side, giving us inversion of configuration of its chiral. SN1, two steps, my leaving group leaves. This first step being my slow step or my rate determining step, forming a carbocation intermediate. That nucleophile, right, with its electrons, then attacks that partial positive carbon. Because that's planar, it can attack from both sides, giving me a mixture of stereoisomers. So the two mechanisms that we're responsible for. Do you know, though, we did this at the end, towards the end of the last video, that often your nucleophile is neutral with SN1, so then you would have an extra step in that mechanism. So the first part I want to look at is the alkyl halide. The alkyl halide is involved in the rate determining step of both our SN2 and SN1 reactions, so it's going to be important for both of these. So for SN2 reactions, again, remember, and we're going to be doing this a lot, going back up, my nucleophile is adding at the same time that that leaving group is leaving. If I look at the transition state, that carbon has 5 things kind of all around it, right? 2 of them are partial bonds, but all of those electrons are all congregated on that carbon at the same time. Because of that, we want the least sterically hindered alkyl halides. So the less bulky it is, the faster it's going to be for SN2. So SN2 favors less hindered alkyl halides. So best with unhindered alkyl halides. So methyl, primary, secondary, and tertiary. For SN2, these are going to be best. So better for SN2. There's just more room. 2 sterically hindered. In fact, we could say that tertiary is really not even going to undergo an SN2 reaction. If you're given the same nucleophile and you're given a tertiary alkyl halide and you're asked which sort of mechanism is it under going to go, SN1 or SN2, do not pick SN2. Tertiary, 2 sterically hindered. To go SN2, just too much stuff there. All those R groups, it just, the nucleophile just doesn't fit in when that alkyl halide is still attached. For SN1 reactions, our arrow is going to be actually the opposite. Remember, SN1 reactions form a carbocation intermediate. More substituted carbocation intermediates are more stable. So since the product of our rate determining step is a carbocation intermediate, we want to form the most stable intermediate. So our rate increases with increasing substitution of our alkyl halide, right? We want to form right? It forms a carbocation intermediate, and more substituted carbocation intermediates are more stable. Know that the more substituted ones are more stable. Since that's the product of our rate determining step, we want to form the more stable carbocation intermediate. Methyl primary, secondary, tertiary. Let's stick to the same color scheme. When I go in this direction, it's better for SN1. And methyl and primary, if I give you one of those, it's not going to go SN1. So given the same nucleophile, if you have a primary or a methyl alkyl halide, pick SN2, do not pick SN1. Methyl and primary alkyl halides. It's not even the alkyl halide, let's say carbocation intermediates. Methyl and primary carbocations are too unstable. We're not going to form them. The only way we would form like a primary one is if it can rearrange to form something better. If it can undergo a rearrangement, then we can still do that. But if there isn't a rearrangement possible, then we're not going to undergo an SN1 reaction with methyl and primary alkyl halides. Also, though, don't forget about allelic and benzylic, right? These guys are resonance stabilized once they form that intermediate. These are also good. They can also go SN2 because they're not really sterically hindered, but these are also good with SN1. So again, the identity of the alkyl halide is going to matter for both of them, right? It is involved in our rate determining step. So the alkyl halide, less hindered, is best for SN2, and then SN1, we want to form carbocations that are more substituted, so we want to use alkyl halides that are more substituted. The nucleophile is the next component that we're going to talk about. And again, remember, the nucleophile is part of our rate determining step, right? Part of our rate law for an SN2 reaction, but not for SN1. So a nucleophile is going to be important in SN2, but not so important in SN1. We're still going to need one, but changing from one nucleophile to another nucleophile is not going to affect the rate. So SN2 reactions require a good nucleophile. Again, remember that the nucleophile is part of the rate determining step. Right? The rate law is the concentration of the alkyl halide multiplied by the concentration of that nucleophile, also multiplied by the rate constant, of course. So SN2 reactions require a good nucleophile. We did learn earlier that charged nucleophiles tend to be better nucleophiles. So we're going to use charged nucleophiles. So something we could do like SH minus, SR minus, OR minus, though once we throw chapter 8 into the mix, that's going to vary a little bit. But we want our nucleophiles to be charged, etc. So the ethoxy, or ethoxide molecule that we used, methoxide, is better for SN2. Something like this, we are not going to use for SN2 because it would be neutral. Do be careful though. You're not going to go into a stockroom and get a bottle of methoxide ions off the shelf. It's always going to be accompanied by some sort of cation. So just be careful. I will give you it like this a lot of the time because I want you to know that it's an ionic compound, right, between sodium and my nucleophile. And if you remember back to your 152 days, those guys are inert, right? A group 1A cation is never going to matter. So if you get those sort of nucleophiles, we're not going to care about that, right? I could give us potassium cyanide, and what we have is, what we have is potassium ions and cyanide ions, but I don't care about potassium, it's cyanide that's my nucleophile. So again, watch out for cations that are hanging out. We could add that cyanide up to our list here. It's a pretty common one. Just please do not get those confused with HCN, right? HCN is HCN. You're not just going to pop off a hydrogen that's covalently bonded, right? That's not a thing. So don't do that. Big red X on this one. So this is neutral, right? It's not the same as CN minus. So if it's a metal cation with our nucleophile, you can ignore it. If it's a hydrogen bonded to it, it's a neutral nucleophile, right? Same with this one. I know I'm making a big deal of this, but I've seen students every semester get these confused. This is not the same as this. So just be really careful. We want charged nucleophiles. A cation could be present. If it is, ignore it. A covalently bonded hydrogen is not a cation, so be really, really careful. Again, every semester I see a lot of students goof that up, and we will do some examples and I will point it out every time, but please be careful. Hydrogens were just not good to take off like that. It's a covalent bond. It's not the same thing as a salt. So for SN2 reactions, since I've gotten way off track here, SN2 reactions require a good nucleophile, so we are going to use charged nucleophiles for these ones. We want good nucleophiles. For SN1 reactions, right, the nucleophile is not part of the rate determining step. So it's not so important the nucleophile is good. It could actually be a not so good nucleophile. So neutral nucleophiles, by neutral I mean uncharged, are fine. So this is where we could use that methanol example, that alcohol, where we could use HCN, that sort of thing. H2S, right? Not to be confused with SH minus. That's a versus. These guys we're not going to do. So neutral nucleophiles are fine for SN1, but not for SN2. SN2, we need a good one. It's part of my rate determining step. The leaving group. So our alkyl halide, it's the halide on the alkyl halide, right? That's our leaving group, is involved in the rate determining step of both SN2 and SN1 reactions. So better leaving group ability increases the rate of both SN1 and SN2 reactions. So a better leaving group increases the rate of both SN1 and SN2 reactions, right? It's part of the rate determining step for both. So remember we had said that better leaving groups are weaker bases. So my alkyl halide bonded to a fluorine, bonded to a chlorine, bonded to a bromine, or bonded to iodine. If we go in this direction, it is a better leaving group. So iodide is a better leaving group than fluoride is. So if you were to compare two sets of conditions where the only thing that's different was a leaving group, so let's say it was the halogen was on the second carbon of 4 carbons in both cases. We had the same nucleophile in both cases, but the only difference was you had a chlorine versus a bromine. The one with the bromine is going to be faster than the one with the chlorine. Its leaving group is better, so it's going to increase that rate. The last component we're going to look at is the solvent. Remember, we can have two types of solvents, polar aprotic solvents and polar protic solvents. Remember, the protic solvents are things that can form hydrogen bonds. So polar protic solvents, these ones are actually going to favor SN1 reactions. Well, polar aprotic solvents, these ones can't form hydrogen bonds, are going to favor SN2 reactions. So polar protic versus polar aprotic, protic for SN1, aprotic for SN2. So some reasoning for that are protic solvents, and again, polar protic. If it's protic, it's generally going to be polar. Remember, these guys can form hydrogen bonds, and they stabilize cations and anions well. Remember that aprotic solvents do not stabilize our anions so well. So protic ones, because they can stabilize both cations and anions, they are stabilizing the carbocation intermediate, which is a cation. They're also stabilizing the nucleophile, which is my anion. But again, because the nucleophile is not part of my rate determining step, that doesn't matter. So it stabilizes the carbocation intermediate. Which is a good thing. This is favorable. Remember that the carbocation intermediate is the product of my rate determining step. If your product is more stable, you're going to be more likely to form that product. So the fact that it's stabilizing my intermediate, again, my first step is rate determining. So this is actually the product, though it's an intermediate, it's the product of that rate determining step. So making that more stable, we're going to push the reaction towards forming it, right? We want to remember that the carbocation intermediate is not our final product. So product isn't really a great word to use here, but it's the best way I can think to get it across. So remember that the carbocation intermediate is the product, it's what we're forming from the rate determining step. Making it more stable is good, right? It's favorable. If I was to look at an energy diagram for this, right? Remember my SN1 reactions, I'm going up and I'm coming back down and then I'm going back up. If I was to, energy and reaction, if I was to add a dotted line kind of showing what happens when I add that polar solvent, this is not super accurate, but it kind of shows it a little bit. I'm actually lowering, right? Lower in energy makes it more stable. If I look at an aprotic solvent, this stabilizes only cation well, which isn't really as important as knowing that it does not stabilize anions well. Remember, the anion in this case is our nucleophile, right? If I'm looking at an SN2 reaction, I have a charged nucleophile. It has a negative charge. If I was to add a protic solvent to it, not aprotic, but protic, it is actually going to stabilize that nucleophile. And in this case, that is not good, right? My nucleophile is what's attacking in the rate determining step. This one might actually be a little bit easier to see by drawing our diagram. So energy going up, reaction going across. It's concerted, so I'm just gonna have one step with no intermediate. So if I was to add a protic solvent, I am stabilizing that nucleophile. This is with protic. Which means if I was to look at my activation energy with that protic solvent, right, it's bigger than it would have been with an aprotic solvent. That means it's going to slow it down. So it's not even so much that an aprotic solvent is good, it's that a protic solvent is going to slow down the reaction, right? If a protic solvent was used for SN2, the nucleophile, it would be more solvated, right? It would be more hidden, it would be less nucleophilic. So the nucleophile would be well solvated and not readily available to attack, right? Our nucleophile would be more stable. In this case, that's unfavorable because it is my reactant. So aprotic solvents the nucleophile is not well solvated and more nucleophilic, right? It's not hanging out with all of its solvent friends, it's actually able to go and do its job. So kind of going back out, or back up, sorry. So SN1 reactions, we're making a carbocation intermediate, and a protic solvent is going to stabilize that, which is a good thing because that's actually the product of my rate determining step. An aprotic solvent, a protic solvent, if a protic solvent, not an aprotic solvent, so a protic solvent for SN2, the nucleophile is solvated, but that is unfavorable because it's a reactant, not the product. So we want to use aprotic for SN2 because then my nucleophile is able to go out and do its job.